Okay, so we're back again. We've been investigating the angle side angle condition. We've looked at it in Euclidean and hyperbolic geometries. Let's look at it in taxicab geometry now. So again, using my GeoGebra sketches that I've built, let's find the one angle side angle. That's this one here. And once again, let's open that in the app. So here's our spherical geometry. There's a sphere. We start, you can see like there's the equator and poles there for reference. Okay, so we have a point here on the sphere, and here we go. We start by going out, I went out a distance this time first, so I started with the side this time, which is how we want to do that. Make an angle at one end, and a ray here, the two rays here, will go all the way to the antipodal point on the other side of the sphere. That's how angles work in spherical geometry. We can measure that angle and generate the rays there. We can move it around. We can move point A around. All right, next we put an angle at the other end of the size of given by this angle, which we can either type a number in here, which will be radians unless you put a degree symbol on it. And that will give you the measure of that angle. We control it by the text box or the slider, just like the other things we've looked at. And of course, where do these two rays meet? This one and this one. Well, we see that they in fact just meet at one point. There's only one possibility. Exactly the same situation we had in Euclidean and hyperbolic geometry. So we only get that one triangle right there, and we can measure the other pieces. If we move this around to a different place, those measurements do not change. If we move B around, those measurements do not change. So in fact, we get the same conclusion that we had in Euclidean and hyperbolic geometry, that spherical geometry, the ASA condition, is enough to make the two triangles congruent if the two triangles meet. One thing's interesting about this one, though, that we don't have in the others, in Euclidean and hyperbolic geometry, since the angles, interior angles must sum to be pi in Euclidean or less than pi in hyperbolic geometry, you can get the angles too big if you're specifying these measurements. So if you specify the first angle and the second angle, if those two added up to be more than pi, that would give you an impossible situation in hyperbolic and Euclidean geometry. That's not the case here. The three angles measure sum to more than pi in spherical geometry. So it is, you can't break it here, right? If it's no matter what your two angles are, as long as they're proper angle measurements, there's always going to be room for that third angle. So you can make these both very big angles, like you can make them both obtuse angles like that, and it's still a triangle. A triangle is possible. See, there's a side, and there's a side. So it is still possible, even in this case, to make the triangle work out. So there is not a zero congruence class possibility here for ASA in spherical. There's only a one congruence class. If you give me any measurements for an angle, side, and an angle, there will be a triangle of that size, and they will all be congruent to each other in spherical geometry. Otherwise, this works the same as Euclidean and hyperbolic geometry.